I think everyone can probably see me here. Once again, if it didn't show up on the chat when you jumped on, everyone is more than welcome to join with their video. Just ask that you keep your audio muted until we get to our Q&A uh, part of we actually are going to have two different Q&A sections in this presentation. One after we present our World Quantum Day kit activities, and then we'll do another one at the end after we talk about the expansion pack activities too. And if you can use that hand raising feature, it's at the bottom there. Should just looks like a little hand next to the little emoji. I think everyone should have that to let us know if you have a question. And I also just wanted to let everyone know that we are recording this. So just to make you aware that you are being recorded, and we will be posting this on our website to share with those who couldn't make it today. So, but welcome. Thank you everyone for joining us. This is the World Quantum Day kit and expansion day pack, the World Quantum Day kit and expansion pack training. For those of you who are getting the expansion pack, you got the World Quantum Day kit last year, which was very similar. And at the end of this, everyone should have pretty much all the same activities. And just a few little housekeeping things before we get going. Like I said, keep audio muted, raise your hand if you do have a question during the Q&A, and we are recording. As we get going here, I want to let folks know that we have several people on the call that are helping with the training today. Our training team today is myself. I'm Molly Iverson. I'm the Youth Quantum Outreach Coordinator at the Science Math Resource Center at the MSU campus in Bozeman. I've met several of you, and I hope to meet many more of you, but I am also the one on the end of most of the emails that are coming through. I'll be sharing my contact info later, so you can reach out to me anytime. I will also have Jeannie Chips, who is our educator professional development lead in my office, who will be joining us later to help talk about our 2D materials activity that's coming as part of the expansion pack. In addition to our office representation, we also have Luke Kohlberg on the call. He is and scroll down and be on the right screen here. Luke is a PhD candidate in electrical engineering at MSU and a Three Forks, Montana native. He builds laser instrumentation for atmospheric science and uses quantum principles like photon counting detectors and laser stabilization as essential tools in his research. So he'll jump in and talk to us about polarization in a little bit. We also have on the call two wonderful supporters from the National Q12 Education Partnership. We have Emily Edwards and Jen Palmer, and they will both be speaking to you in just a little bit here, talking you through a bunch of these activities, which I shamelessly borrowed from their website, the Q12 Partnership website. But just to introduce them quickly, Emily Edwards is an associate research professor in the Department of Electrical and Computer Engineering at Duke Quantum Center. She is primarily interested in science communication and informal STEM engagement. Informal STEM education with a focus on increasing adult and youth interest and engagement in quantum information science and engineering topics and technology. Meanwhile, we have Jen Palmer, who is a curriculum specialist in the Department of Computer Sciences at University of Chicago. Her work focuses on supporting K-12 teachers and students with an emphasis on computer science and quantum education. And you guys, thank goodness they're here, because I am not a quantum expert. I am a science educator with a background in geology. So I'm happy to have some support today. Moving along here, I gotta figure out my own navigation. Here is a quick intro to why we are going to move quickly. We have a lot to cover. We're going to be going through, after my little introduction here, I'm going to turn it over to our Q12 partners to talk about what is quantum, World Quantum Day, and the International Year of Quantum. Then we'll go through the kit materials, each activity one at a time. And at the end of that section, we'll have a Q&A before we move into the expansion pack. So if you didn't get the expansion pack and you need to jump off, that's totally fine. Just a quick introduction. Why are we bringing you this quantum kit from Montana State University? Well, whether you are aware or not, quantum is a big deal in both Montana and at Montana State University. We have several research grants that are quantum focused or have a quantum component. We have several centers and researchers on campus who incorporate quantum into their research, or are actively studying new quantum information systems, quantum computing. My list here shows a few of those. The grant I'm working under is the Q-Core grant. It's the MSU Applied Quantum Core. We have Spectrum Lab. We have Optech, the Optical Technology Center. The Monarch Foundry, our 2D materials activity, has to do with this idea of actually creating and manipulating materials at the quantum level. And Montana, in and of itself, is a tech hub. We are designated through the government as a place where technology and quantum optics and photonics are all really a growing enterprise here, and research and entrepreneurship are working hand in hand. We are actually going to be, I believe, the only university. If anyone knows otherwise, please call me out. But to have two working quantum computers on campus shortly. So we are actually right at the forefront of some of this technology that's coming out. That little graph there shows the growth over the last couple of decades of photonics and optics industry in Montana, with quantum being added to that. So just if you were wondering why this is something that's going on in Montana, this is why. Very quickly, too, a couple of upcoming events I mentioned in emails I've sent out. We have on World Quantum Day next Monday, we will have some of these lovely support help joining us again, people who know more than I do about quantum, who can actually say, you can ask me anything about quantum. We'll be doing a webinar that day that I'll be sending out an invite to. And on Wednesday, the 16th, if you happen to be in the Bozeman area, we have a local from Missoula, Mr. G, will be doing a quantum laser and science show here in Bozeman at the Wilson School Auditorium. And then lastly, before I hand this off, we also want to put a plug in for our Quantum Summer Teacher and Student Academy. Some of you I know are already signed up, but if this is of interest to you, we'll have a week-long camp on our campus in Bozeman in June. And then in July, we'll be hosting the Montana STEM Summer Institute. It's in its 7th year now, which will also have some quantum outreach and education opportunities. So that was a lot quickly, but I want to give the folks who have more to say than I do the ball right away here. So I'm going to switch this over and go ahead and I'm going to turn my own mic off and turn it over to Emily and Jen to tell you what quantum is.
Great. Thanks so much, Molly. And thank you for organizing this. And mostly thank you to our attendees for coming to this webinar to learn about the kits, to learn about quantum, and to learn about how ways that we're hoping to support teachers across the US bringing quantum to their classrooms. So I'm Emily Edwards, and I'm often in a superposition of Duke and UIUC because I used to be at UIUC in Illinois. I live in Illinois, but I am a professor at Duke University. I have a project that's supported with UChicago and Pitt and a whole collection of people, which I'll show in a minute, that is supported by NSF and the Army Research Office to help teachers bring quantum to their classroom. And mainly what we do is exactly what we're doing today, which is to try to find ways to lower the barriers for you to have quantum in your classroom, both informally and then down the road formally through curricula as appropriate. And so this is federally supported, and so I always like to acknowledge that because it's a very important component to how we're able to do this, working with states. Next slide. Because I'm not in charge of the slide. There we go. Okay, so the Q12 was established in 2020. And it was established by actually OSTP and NSF to partner across the ecosystem to achieve a diverse and quantum ready workforce and to increase public literacy in quantum information science. And they convened a bunch of industry and professional societies, but really at this point, I would say Q12 sort of, we try to just be a way to convene collaborators and anybody interested in this space to see how people can support teachers. Truly, that's, I always try to say my goal in life is to get quantum into STEM education, and B, give as much money to teachers as possible when I have the power to do it, which is not often. But I do try. So that's what this program is. And so Jen is part of the U Chicago part of this collaboration. So thanks, Jen, for being here. Next slide. Okay, so I did atomic physics. So I love science communication, but long time ago, like maybe 15 years ago, I received a PhD in physics, in atomic physics specifically. And back then we just called it atomic physics, but now we use quantum for all of this space. So it's kind of funny how the vocabulary changes in this. But when we're talking about quantum and quantum information science, specifically, and when we're talking about quantum and quantum education, oftentimes we're talking about things that are very small, like atoms or subatomic particles, or really cold, near absolute zero, or both of these things. Quantum theory encompasses a lot more than this, things that are small and things that are cold. But for the purposes of this, I think this is a good starting point for a lot of people to think small, think cold. And we made a video about this a couple of years ago for World Quantum Day, and that video, we'll have links to that later. So that's one place you can start sometimes with students, is to show them videos that give them kind of an orientation to the where and what quantum is. For a long time, it was mostly part of physics, but today quantum information science is much more than that. It's about controlling purely quantum features to improve technology, do science, and solve problems. And it's a highly cross-disciplinary field. So, people working in quantum may have degrees in computer science, in physics, in engineering, in chemistry, in mathematics, and a lot of different STEM areas. And that's just the people maybe doing the science and engineering. There are, of course, people working in policy and education. And so it's quite a broad space now that students can think about careers in. Next slide. So another way we orient teachers and students to quantum is to think about, okay, so it's small and cold, but really, is it new? Is it different? And the answer is no. We're celebrating, technically, we're celebrating 100 years since a particular set of papers came out in the 1920s with the International Year. But in fact, quantum's been around, really, we think of it as starting in the early 1900s. And in the 20th century, our understanding, like using quantum theory to understand nature, to understand those things that are very small, we often can't see, to understand those effects, we developed this theory, quantum theory, and it paved the way for lots of technologies. So MRI machines are based on our understanding of how nature operates in this way. And so semiconductor industry is based on advances in quantum theory. Lasers are based on similar advances in quantum theory, and GPS, the Global Positioning System, uses atomic clocks, which are kind of at the intersection of 20th and 21st quantum technologies. And those clocks are highly precise and allow us to really find our locations very well within, just a few meters even. And so all of these are examples. There's lots of examples like this where quantum is kind of hidden in technology of the 20th century. Next slide. But in the 21st century, people stopped saying quantum physics as much and calling it quantum information science to really recognize that we're doing something different or something more really additional. And so in the 21st century, what I think is exciting a lot of students, what I see exciting teachers like yourselves, what I'm seeing exciting policymakers and just folks around the globe, is this idea that we can go beyond understanding nature and doing kind of complex but relatively theoretically simple advances to being able to control nature at things like control entanglement and superposition, which are fundamentally quantum features. So in the 20th century, people like understood that there was things like superposition entanglement, and some of these kits talk about superposition, so you're going to hear that word throughout. We understood that existed, but we weren't really controlling it to speak of. In the 21st century, we want to control superposition entanglement to improve our ability to do computation, our ability to do sensing, and our ability to communicate over long distances. And so this opens up a range of applications, just like in the 20th century, but these applications are really in security, a lot of understanding more about science, understanding more about nature. Molly mentioned geology. There's some applications of quantum sensing in geology. And then being able to really not just look at encryption, but also communicate securely. And so these are things that are really pressing issues of today, and quantum will hopefully contribute to these areas. Next slide. Let's see. There we go. Okay, so Quantime is meant to, so that's my brief. What is quantum? And then why it's exciting. But Quantime, we developed this program to try to give teachers something now to put in their classroom. And so because we know that changing curricula is really hard, we know it's really difficult to figure out these new and emerging technologies. So what the purpose of Quantime is to kind of lower the barrier by providing activities that have been created by scientists in partnership with teachers, and have those activities be readily available to you, and that you can get maybe an hour of training like this, or even if you don't have time, you can just look at a facilitation guide. And if there's a day during the school year that you want to introduce something new, these are supposed to be ready to go for you. Now, it's an imperfect system. And so we've been doing it a couple of years, and but it so we always want to ask for feedback from teachers on how it's going. And so we try to, get evaluation. So if you see surveys that they often come from my email address, asking for feedback on Quantime, then I encourage you to participate so that we can improve this program. So there are lots of options, and the kits you have are part of Quantime. And I think some of the activities were made by, one of them was made by Jen, I think. Some of them were made by University of Wisconsin. And I'm not sure what other ones there were. So the point of this, though, is we try to collect what's going on in the ecosystem, like across the country in this area, and all the activities that are developed, and we try to get people to package them for your classrooms. So that's the whole purpose of this program. Next slide. And so what we did was we made we could sort of curated and polished some activities that were out there. And then we also have, Jen has happily made some nice choice boards around the activities, which are not shown here, but and then we have stickers. There's supplemental stuff to go with Quantime that you can see on our website. And then also beyond the kits that you receive, there are more activities. So there are online activities, say more targeted at computer science classes, and there's really informal game activities. So there's a lot going on here, and we'll keep adding. So I encourage you to visit and see what else is out there. And then if you try something, you're like, this one was not as good as that kit, just shoot us an email. And we'll do our best to, this ecosystem's pretty small, so we're able to kind of at this point pull a lot of levers to improve this stuff to work for you. Next slide. Okay. Oh, those are the choice boards. Thanks, Jen.
There are 2 pages of them.
There are 2 pages of this.
I'll talk about them. I wanted to highlight that we had, can you go back to the previous page?
Okay.
Molly. We wanted to make it easy as Emily's introduced quantum and why we have all these little activities and why it's important to bring it in your classroom. It's still a concept that perhaps we haven't all studied in depth. And so we wanted to make it easy because it's one more thing on your shoulders otherwise. And we wanted to make it easy for you to select an activity at any grade that you are teaching. So we have created these teacher choice boards that give you a menu of activities. Some are hands-on, some are online games. Some are as simple as reading a zine or watching a video or creating a thaumatrope, which is one of the activities we're going to talk about today. So they are organized by either concept or grade band. And if you go to the next page, you'll see that we have some for entanglement. So again, like Emily said, you're going to keep hearing about superposition and entanglement and qubits. And we are going to be creating some custom choice boards this week for the activities to kind of fill in some small things that are fun add-ons to the activities that we'll be introducing today. So if you want something besides the hands-on stuff from the kids, we have some more things coming for you. Okay, next slide.
Okay, and then I will say, in addition, one of the things we do have, I mentioned that video, we have actually 2 videos that try to emphasize this role of role models. And so there's not a ton of material out there currently on quantum careers and quantum role models. One of our funding sources, the Army Research Office, did support us to make some stuff. So hopefully this summer and in the fall, we'll have more on that. But for now, if you're looking for stuff, videos to show in your classroom to go with this, we have these, and then we'll be adding more that are from the ecosystem. But this is an area that hasn't been developed much, but I did want to highlight it. We think it's really important for students to see themselves in these careers that are very unfamiliar and maybe they haven't heard of. And so would love to hear what's useful in this vein as we're developing more and more material around careers. Next slide. Okay, I'm just going to say a few more words, which is first, next slide. So there are 2 things. There's the International Year of Quantum, so happy International Year of Quantum Science and Technology. And that's this year, 2025. And then every year in the past, say 4 years, there's been World Quantum Day, which is April 14th, which I think this is celebrating both of these things. So, so first I'll say that I mentioned the International Year recognizes this 100-year mark since the development of some of the theory of quantum mechanics. And you can learn more about that at quantum2025.org. You can also, I encourage you, you could just send me an email. I'm involved in this one in particular because I'm on the committee for it. And so if you're like, how do we keep celebrating? I have questions. I'd be happy to connect you with whomever, but if you're unsure, just send me an email. So it's a very exciting time. The UN actually designates international years, and then they're run with UNESCO. So hopefully there'll be even more stuff that comes out for fall. Next slide. Oh, and that's what I just said, so we can skip it. There is this, okay, so I will say we have a mascot that was created by a cartoonist. Her name is Quinny, and she was just shown on the previous slide, but we will share these slides. And so, it's kind of a fun all-out effort. So World Quantum Day, that's Quinny. So that's Quinny. So it was really fun that we had a cartoon even made for it. So, and we're just going to skip this, Molly, because I think we're getting close to time. So I just want to keep us, there we go. World Quantum Day. So actually World Quantum Day predates International Year, and in fact was an important way to highlight the visibility of this field and give UN the necessary information they needed to be able to declare the year. So it's a separate initiative. It was started in Europe, but the US heavily participates. And in fact, Quantime we've always held Quantime in conjunction with World Quantum Day to try to give another reason to celebrate. Now we run Quantime all year long, but originally it was aligned with World Quantum Day. So we're excited that you're doing this for this activity, and it's grassroots. And I will say that Quantime and the effort that you're doing and other teachers around the US, I think is the most active sort of quantum in school initiative around World Quantum Day. So we really appreciate your participation. Next slide. And that, oh yeah, there's the video. And so that we put the videos in, not to really show them, just so you would have links to them to share. And that's, I think, wraps up these slides, this section.
Hi.
Yep, there we go.
Okay, thank you. All right, thank you very much. Actually, that was a great lead in to where we're going next here. So I am going to switch over back to the tab I was on before. Hopefully you can all see that again. And we are going to, hopefully, let's see, we can get back out of here and get to the video. I made a very short video showing what is in your World Quantum Day kit because, as Emily mentioned, we included several Quantime activities in here, and all of that information is available to everyone online. But in addition to that, we also included a couple of activities that are a little more, I shouldn't say completely specific to MSU, but that have been developed in their own particular way through MSU, both the one that Luke's going to present about polarization. There are some polarization activities on Quantime, but we are going to go a little bit deeper than that and what Luke's going to show you, and then same with the 2D materials. So hopefully, please give me a thumbs up that you can hear this, but we'll play this really quickly just to give you an idea of what's in that kit. Your World Quantum Day kit looks like this. When you open it, you will most likely find some papers on top. These are an overview of the kit materials with a bit of information about quantum, World Quantum Day, and the International Year of Quantum, a flyer about our upcoming Quantum Summer Academy for students and teachers that will be happening in Bozeman the week of June 16th, and a flyer about the upcoming STEM Summer Institute scheduled for July 28th through 30th, also at MSU, where there will be more quantum opportunities. You will also find in the bottom of your kit 2 booklets. These are reports about quantum workforce needs and opportunities in Montana, and a report from the quantum convening our office held in Bozeman in October 2024. We've also included a World Quantum Day poster for your classroom. Another extra we've included is a bag with some different stickers. There should be enough World Quantum Day and Schrodinger's cat stickers from the Advancing Physics Society for all unique participants. There are a handful of iMod stickers. The iMod website has a quantum education portal with more activities. You will also find Molly, the Youth Quantum Outreach Coordinator's business card, as well as contact information for folks at the National Q12 Education Partnership in the bag. Q12 Education Partnership in the bag. Now we will show you how to organize your activity materials and printouts so they are easy to use. You should find the 3 polarizer demo activity sheet along with a bag labeled polarizer demo. You should have gotten 3 polarizing sheets. Some, but not all polarizing sheets, have a protective film that needs to be removed prior to the activity. You will find both a bag and a printed packet labeled thaumatropes. In the bag, you will find colored pencils, tape, and enough index cards and straws for all the unique students you told us you will be working with. You will find 3 printed packets of paper with the Wonder of Quantum Physics logo. The first, labeled Introduction to Light and Quantum Computing, provides background information useful for both activities. You will find a printed activity and 1 bag of materials labeled Electron Transitions, which includes flashlights and glow-in-the-dark stars. You will find another printed activity labeled Exploring Spectra. This activity has 2 bags of resources. One contains light bulbs, the other diffraction gratings, and some other materials. I'm sorry, that was a little slow. That was working with some old software on my end. However, I hope that it's helpful. Just, I know a lot of times when you get a kit and there's just a lot of stuff in there, to try to figure out exactly what you're using. Now we're really going to dig into that, and we're going to go through each of those activities that we pulled out. I'm going to turn it over to Luke Kohlberg to kick us off with the 3 polarizers demo.
All right, awesome. Thank you, Molly. So one thing that I've come to learn about quantum mechanics is that the math behind it isn't any harder than in any other type of physics or chemistry. It's just built on ideas that are unintuitive the first time you see them. The real challenge is wrapping your head around those ideas and getting started. And that's why I like this demo. It's simple and it reveals one of the most important and unintuitive principles in quantum physics: superposition. To understand this demo, we first need to understand polarization. You all have polarizers in your kit, and if you're planning on trying to do this along with me, it's time to take that protective film off now. You can also just watch for now and try it yourself later. So before we begin, let's take a moment to review polarization with a quick slideshow. What we call light is an electromagnetic wave. It's an oscillation of electric and magnetic fields. On the slide to the right, you can see the geometry with the E field, the electric field pointing in one direction, the B field, the magnetic field pointing in another, and the whole wave traveling perpendicular to both of them. Next slide, Molly. So now that we know that light is an oscillating electric field, let's talk about polarization. The polarization of light is defined by the direction that the electric field, the E field, oscillates. If you imagine the electric field vector as a function of time, the set of points traced out by the tip of the vector is the polarization. Here on this slide is a vertically polarized wave. The electric field is always pointing straight up and down as the wave travels forward. More generally, the polarization can point in any direction perpendicular to the direction of travel: horizontal, diagonal, circular. Each of those is a different polarization state. Next slide, Molly. Now let's shift to a quantum perspective. In classical physics, we describe polarization as a vector. You can add 2 vectors together to get a new direction. For example, on the top, vertical plus horizontal gives you diagonal. But in quantum mechanics, we say that a photon, the quantum unit of light, isn't just pointing in a single direction as it travels. Instead, it's better to think of it as traveling as a combination of all the electric field directions that could possibly add up to form the wave we observe. That's what we mean by superposition. The photon is in a blend of multiple possibilities at once, not either horizontal or vertical, but both in some weighted combination. The act of observing the polarization, however, forces the polarization to pick a polarization direction. It travels in a superposition, but when you observe it, it arrives in a single position. Next slide. Now here's where the polarizers come in. A polarizer is a filter that blocks light that is polarized in one direction. They're commonly used in sunglasses to reduce glare. Whenever a photon hits a polarizer, it faces a choice. Does it match the polarizer's axis? If yes, it passes through. If not, it's absorbed. In quantum terms, this is a measurement, an observation. The photon, which was in a superposition of polarization states, is forced into a determinate state. It either collapses into the allowed direction and continues on, or it's blocked entirely. So polarizer isn't just measuring the polarization, it's changing the polarization. Though the photon's polarization is a blend of possibilities, if it wants to pass through the polarizer, it must choose one single polarization. All right, let's get to the experiment. So Molly, can you stop sharing? And this will probably work best if you all in your layout switch to the stack view. So I'm large and you can all see me. Can everyone see that? Molly, can you give me a thumbs up if you see that? All right, perfect. So I have 3 polarizers here, and I've built simple frames for them using binder clips and rulers. And this activity works best as a partner activity. It's a lot easier to do when 3 students each hold one of the polarizers, and it takes a bit of dexterity to do it by yourself. I'm going to turn on this work light in the background so you all can see what's happening. All right, and if you try this yourself, you'll notice that the computer screens are actually polarized. That's a fun bonus observation. So to begin, I'm going to start off by demonstrating the 2 polarizer experiment. Most light we encounter that we see is, unless it's being reflected or coming out of a computer screen, is randomly polarized. That means it contains electric field components in all directions perpendicular to the direction that the light is traveling. When randomly polarized light passes through a polarizer, only the component aligned with the polarizer's axis passes through it, in this case vertically. The rest gets absorbed. So the first polarizer acts as a kind of preparation, converting the random light into polarized light along the axis. If I take a second polarizer and align it with the first one, let's say both vertically, no additional light is blocked. The light that made it through the first one is already aligned with the second one. But if I rotate the second polarizer 90 degrees, now it's horizontally. The 2 are crossed and no light gets through. What's happening is this: the first polarizer conditions the light into a vertical polarization, and the horizontal polarizer, the second, blocks anything that doesn't have the horizontal component. Since vertical and horizontal are perpendicular, the vertical light has no component and it's completely blocked. If I start to rotate the second polarizer to a non-zero component, we can see that some of the light makes it through. Okay, now let's introduce third polarizer. This is where the quantum weirdness begins and where having a partner really helps. So I'm going to take these 2 polarizers and cross them. And then I'm going to introduce the third polarizer. Before I do, I want you to, in your heads, predict what's going to happen. If I cross the 2 polarizers and I insert the third vertically, will light make it through? Excuse me.
I should have been there with you, Luke. Sorry.
Right. No, it's all good. So if I enter it vertically, will light make it through? No. What about horizontally? Also no. All right, now what about diagonally? Yes. So why does this happen? This happens because the first polarizer conditions the light into a vertical polarization state, and as it travels towards the second diagonal polarizer, the photon isn't locked into that one state. It's in a superposition. It travels in a superposition of all possible polarization vectors that can make up that diagonal. When it reaches the diagonal polarizer, it collapses into that diagonal polarization, and only the component of the electrical field that aligns with this makes it through by being forced to adopt a diagonal polarization. After passing the second, it's now traveling in a new superposition. And when this light reaches the third polarizer, the horizontal one, it again collapses, this time into a horizontal polarization. And now it does have a component that can pass through. In total, half of the electric field makes it through. And since our eyes see power, which is the square of the electric field, we see 25% of the original light. So what have we done here? We've effectively rotated the electric field, not by twisting it directly, but by leveraging the quantum property of superposition. The photons are traveling in a blend, a superposition of many possible polarization states, and at each step, each polarizer, they're observed, they're measured, and that measurement forces them to collapse into a specific state. And that's the deeper lesson here. In quantum mechanics, measurements don't just observe, they transform. When you show this to your students for the first time, some of them aren't going to believe it. And that's okay. In fact, it's expected. When people first encounter ideas like quantum superposition and the role of the observer in quantum mechanics, they're going to be confused or they're going to be convinced that something's gone wrong. That's how I was the first time I saw it. And honestly, there's no shortcut for that confusion. The first time they see it, they'll be confused. The 10th time they see it, they'll start to make sense of it. And by the 1000th time where I'm now, it's completely routine. So that's the journey of learning quantum physics, and this three polarizer demonstration is a great place to start. All right. Thank you all for your attention. I'm going to turn it back to Molly.
Thank you so much, Luke. I really appreciate this. I was able to watch this polarizer demo sort of live on screen from someone else who did it. But then I had to go seek out Luke to show it to me again. And now you will have it recorded on this training, so you can go watch it several times over and hopefully start to fathom this weird quantum stuff that I'm not quite there yet. But I'm going to go ahead and share my screen again. I believe Luke is going to stay on so that he can answer questions. That's great. Thank you. And now I'm going to go back to the Quantime presentation. And this is where I landed. Does that look like a good starting point there, Jen?
That is perfect.
All right.
There's my thumb. Okay. Next slide, actually. Thank you. So a perfect follow-up to Luke's polarizers activity is one that we have for students in grades 3 through 5. We want to make sure that young students start to build intuition about these concepts that are not kind of aligned with what we experience in our everyday lives. We don't see superposition. So how can we explore these ideas and kind of get people thinking and acclimating to them? So one of the things that we're going to do is make thaumatropes. So we're going to introduce superposition and measurement through creating thaumatropes, and also looking at some optical illusions that are two things at once, right? As well as then you can use these to introduce the difference between classical computers and quantum computers. So you're going to be, in your kit, you will find a copy of the lesson plan, straws, index cards, tape, and colored pencils. These are all the creative components for your activity. And next slide, please. Oh, and this was created as part of the EPIC project, but is posted on the Quantime site. And you can actually just go to the next one. There we go. All right, so go ahead. And we start the activity by inviting students to say, what do they see? They see a duck? Do they see a rabbit? And go to the next slide. You just kind of tab through a tiny, so we there are many slides here, Molly, so you may want to keep your hand by that. Okay, so you're like, bat. All right, next one. She dropped the bat and ran to first base. And then we have this whole series of slides that introduces this ambiguity between the meaning, and the word is in a bit of a superposition, right? It has two meanings until we know what the context is. If you can go to the next slide. So we talk a little bit about how it's unclear, if you're just seeing the word bat, what the meaning is that was being used in the word, which interpretation. But once we see the person running to the base and know the rest of the sentence and understand the decision is made forced, and there's only one interpretation. We know they're talking about a baseball bat. You didn't drop the bat and run to first base, right? So when you just see the word, it's unclear. When you see where it is being used, it's obvious, or then you can make the choice. Can you go to the next slide, please? So, but what is this idea of quantum measurement, right? And this introduces students to this idea that measurement, well, in here it goes on what I just said, context clues. Sorry, go on. Feels funny to not be doing my own slides. All right, so thaumatrope is a word I did not know before making this activity, but somebody else in my life was familiar with them. It's an old-fashioned optical toy. It creates an illusion of two things spinning at once. I have an example of the one here. I can't see it myself. There we go. And so if you spin it, you can kind of, I don't know how well that shows up on the screen, but you can see the soccer player kicking a ball to the goal. So you can go to the next one. So we ask students to create this physical example of a superposition, and all of these slides, are included in the lesson plan. And there's also a teacher lesson plan that has goals and background information for you and everything like that. So we invite students to create their own, design one, share them with their classmates. You can go to the next one. Yeah, so we ask them to share them. And then we make this connection to quantum computing, and that this idea of something being two things at once can be used in computation and can be and can enable quite a powerful advance over classical computers. And we get a little bit into how classical computers store information as zeros and ones using bits. And so it's either a duck or a rabbit, a 0 or a 1. And quantum computers have this ability to have this superposition of the duck rabbit, right? You can go to the next one. And so they have, there are currently unsolvable problems. There are unsolvable problems, things that cannot be solved with classical computers, even the fastest kinds of supercomputers that we have, just by virtue of the way that classical computation works. And so for some types of example question problems, we expect quantum computers to be able to help solve those things that were previously unsolvable. Okay, go to the next slide, please. And I guess that's the end of our slide deck for this activity. Yeah, thank you. Does anybody have any questions about bound trips? And actually, I have no idea if we have any third through, if anybody put in the chat what grade you teach, I would love to know.
I think we do have, I think we do have a couple of 5th grade teachers that
Okay.
they may or may not be on the call, but I will also say that I've used this lesson with slightly older age group or as an introduction to for even the older kids into superposition, and it's a great way to get them thinking that direction.
We always take this as like a really easy activity to start conversations at like outreach events and things like that, because it's good not just for little kids to stop by, but just introducing the conversation and starting the conversation. Yeah, it works with lots of grade levels. Thank you.
Awesome. And now we're going to move on to exploring spectra. So you can easily just say next to me and I'll click right on it. I'm not sure which of the two of you is presenting this one.
I think I'm doing this. Is that
Yeah,
right,
sure.
Jen?
Mm-hmm.
Okay. Yeah, so, and I also, Molly, and for everyone, I've been adding some additional helpful links into this slide deck as Jen and Luke were talking. So I put some helpful stuff on polarization that's additional background. And then I also have a colleague who's a little obsessed with this, and he started making magnetic polarizer, like kaleidoscopes, to be able to do this, you know, awkward thing that Luke was doing, and then has made some videos with his younger child. So I put some of that stuff in, and then we also have like a JavaScript version of this. In case, you know, the polarizers get messed up, we have a digital version of this. Hang on a second. I have a kid that just showed up, so maybe.
Well, while she
Jen will
pauses,
say
I will tell you, I made a Scratch version, a Scratch programming version of this Thaumatrope activity, so kids could also make digital like Scratch Thaumatropes if they're doing Scratch programming.
I have to do this.
Awesome. This is what I love, because I've found in my whatever it is 5 or 6 months of work in quantum now that there's so much stuff out there, and just stumbling upon it takes a while. So I will also add that I'll go back through this presentation and take all of those links and put them in a document so that you don't have to plow through the slides to look for them either. But I super appreciate you guys adding things.
Great. So this this activity, exploring spectra, is one that many groups have done. And so while I'm going to show you the one, walk you through a little bit, the one that you have the materials for, there are various groups that have also written teacher guides. And I think I've added a link to at least one that I know of that uses a different sort of approach, in case that works better, you know, use what works for you. So the materials here is you're going to have a bunch of different light sources. The Montana folks were kind enough to provide light sources. If you want to do this next year and your light sources don't work, you can find them just have students look at any light source. The only thing is diffraction gratings. I've had to put warnings on everything because sometimes people have diffraction grating glasses and they look like the solar eclipse glasses. And so I've just always now warned people that students, of course, should not look through these kind of filtered material, whether it's polarization filters, diffraction gratings, or anything else at the sun. And so yeah, they have all these light sources, and with the laser pointer specifically, they should really not look, again, mind the safety on these. I don't want to scare anybody, but I'm just saying mind the safety instructions. And I will say this one and the next one, when I saw this, I was at a teacher PD event in California a couple weeks ago. The flashlights that were sent to that group were very bright, so just mind the brightness. So the goal of this one is to show, so Luke talked about the polarization, sort of the waviness of light. And this one builds on that concept. It doesn't necessarily talk about polarization. Next slide. Okay, this is the Exploring Spectra. These are what you can, there's a student guide, an intro to computing, and a teacher guide that Molly already said you have. And then I've added on the links that you'll get shared is this one doesn't use the 5 E's or the 3 E's approach to teaching. This one walks through some concepts and then it has some questions on it, but there is a teacher guide that you'll have a link to that if you're used to the 5 E's or the 3 E's, it'll use that instead. Okay, so next slide. So, okay, next slide. I think these are, okay, so the other thing is it's good to know that some of it is good for upper grades. So we found, like just from teachers giving feedback on this, that the diffraction grading one works for a lot of different age groups. The electronic transition one, actually, while younger students really enjoy it, it's more appropriate given the material that students know. I think they'll understand it a little better at the upper grades. Those are the disclaimers I said at the beginning. So in this particular teacher guide, the material talks you through what the spectrum is and introduces students the idea of the electromagnetic spectrum and the idea of diffraction. But it's not necessary if you're used to doing the more explore first and then give them information. You can go in whatever order you want. So the next slide. Okay, so this is a bunch of NGSS stuff that you have in your guide if you want to look at where it pairs in. The first activity that this spectrum one is more well matched to the curricula, I would say, than the electronic transitions. The electronic transition one matches more to a chemistry curriculum, actually, than a physics one, just because it talks about photons, and photons are sort of the boundary of what is in NGSS. All not necessary, because but sometimes, because these are informal, it's not totally necessary, but I think teachers really, in our experience, like to know in case they want to use this as part of their curriculum. Okay, so Luke did a nice job talking about how light's a wave. Next slide. Okay, what he didn't mention, and so what I'll do to build on that, is that light can be separated using a prism, and it's composed of constituent colors. Now, there are different types of light sources, so not all light is white light. This is showing white light. And so you can see this spectrum, and the spectrum tells you something about the light source, but it also, while this particular guide does not go into it, it hints around the idea that light, being able to see a spectrum, is like a fingerprint for objects. It's a fingerprint for the type of light, but it's also actually a fingerprint for the source, like the material that made up the source, for instance. And so that's it hints at that, but doesn't say that specifically, but that might resonate with students if they're familiar with light sources like sodium lamps that are yellow in parking lots. They're like that because of sodium specifically in its spectra. Next slide. Okay, so more on this fingerprint business. So while you can separate light out in its constituent colors, which is what students are going to basically do with the diffraction grading, you can you know, those colors belong to the electromagnetic spectrum, which the electromagnetic spectrum is sort of all the light you can see and all the light you can't see. It's any radiation that's out there, and it's classified according to its energy. And so that's what the spectrum is. And so we can only see, of course, a small portion of it. Humans can only see a small portion of it. And we're kind of peaked around the green area, actually. And so, and different materials will respond to different kinds of light, and that kind of, these two, this one, the diffraction one that I'm talking about, and then the next one I'm going to talk about, both build on this idea of the electromagnetic spectrum, and then how different light can interact with different kinds of materials. Next one. Okay, so in this one, you have a bunch of stuff. We've talked about that. The diffraction grating is just like a little, you know, I think you guys have the square type. Is that right, Molly? Okay. So here's kind of what you're going to see. So if you could play this video, this is courtesy of the Wisconsin people. Okay, it should get, you can kind of, let's see, hopefully it'll show the actual demo. Let's see. Oh, here we go. Here we go. So you're going to walk through and have students look at the different spectra. I'm going to shut my door. It's that time of night when all my children come in and out. Okay, so then looking at this one's looking at like a light bulb, and you see it's this like pretty array of rainbows. It's pretty distinctive from a laser. And then the fluorescent, well, I thought that was the fluorescent one. I guess that was the LED one. The last one was the LED one, because this one makes more sense. This is the fluorescent light one. It's very similar, but it's got a kind of a different pattern to it. Okay, next slide. I apologize for the yelling children in the background. Okay, next slide. I think it's just stuck on this video. Okay, so then your packet kind of walks you through what's happening here, and I think I kind of hinted at this, that animation's like the best explanation for what's happening. What's nice about this is students will see like that lasers, we're trying it with a laser, but it looks, sorry, I didn't see the comment.
I think they might be using a different color laser in the demo than
That's right.
They were given a red one, so.
That's right. The laser in the demo was using, the laser in the demo was a green laser.
It looked red, but then it said, see how it looks green? I wondered if it had to do with the cameras. I didn't know why it was green.
Okay, the red laser should look red. Is the red laser looking red? In the, Linda put in the chat.
I think it is. Linda, you're welcome to unmute and tell us what's going on.
Perfect.
Yeah, it's red. So I thought the red was supposed to look green, which sounded amazing, but so if it's red, it's supposed to look red.
It's supposed to look
Right.
red. A red laser, yeah, I don't know. I was also confused when I watched that video. I watched it earlier today and was like, this is confusing. Feedback for the Wisconsin people.
I was waiting for their follow-up explanation about how cool, I was like, what a neat phenomenon.
No, I mean, right, that would have been, no, it's unfortunately, no, it's not filtering. So the red laser is red because it's only made red, or laser, all lasers are monochromatic around kind of a specific color. So there are green lasers, there are red lasers. Now, sometimes there's other kind of radiation that emits from a lasing device, like a laser, but the color that it's lasing at is a single color. And so diffraction grating separates out light into its constituent colors. And if it's red, it's just going to be, there's no other way to break it down. And so that's why it should just be red. The other ones have many colors in them, and so they should separate out into a rainbow, and they're different types of sources. So the question Michael asks is, does the fluorescent light give a mercury spectrum? That's a really good question. I don't know. A fluorescent light, is it made, if it has mercury in it? That's a good question, but it's not monochromatic, but it is, if it has mercury in it, probably has other stuff in it too. So this is a good question that now I'm going to have to look up. Nobody
want
has
me to
ever
take that,
asked that
Emily?
question before. Luke, did you unmute
You
yourself?
want me to answer that?
Luke knows the answer. Luke, let's hear
Yeah,
it.
so a fluorescent light has mercury in it that produces mostly ultraviolet light that then will pump white phosphor. So you're going to see a white spectrum from the phosphor primarily, but it might look stronger in the mercury lines. So there's kind of a two effects going on in there.
Thank you. All right, next slide. Okay, so now it's going to have a bunch of discussions, and I actually know that one of these slides explains the differences between the different ones, but Luke actually did quite a good job. So, so the main thing here is that students we know are going to want to play with the light sources. So you're just going to have to kind of mind the light sources some. And then, yep, there we go. So the other part is it does help to be in the dark. So so you should turn out the lights for this or have low lighting except for the source itself. It does help a lot with the visibility. So if you're like using like in that video, it had the lamp on the table, but the rest of the room was kind of dark. So that's kind of the best setting to see it in. And next slide. Okay, so this actually goes, there you go. LED and fluorescent light bulbs come from light bulbs. And so then it explains a little bit of this thing that that Luke just said. And then, so the rest of this, because I know we're out of time, is a lot of like common questions that you get asked. And I think one of the things that are important about this is that there are lots of other types of light sources. So one of the other guides that does this, they do this with glow in the, not glow in the dark, but like, they're like those light up sticks, those light sticks. Just check on those too. So any light sources will really work and enhance this activity if you have other stuff. Okay, so the next activity. This one is one of the most popular activities we see teachers doing in their classrooms. And so this one is also from the Wisconsin people and supported by National Science Foundation, one of the quantum centers. And so this idea, this one is one that can take students from the idea of something that's glowing to the idea of using electronic transitions in quantum information science. So Jen did a nice job of talking about qubits being either a duck or a rabbit, a 1 and a 0 or a 0. And those ones and zeros in atoms map onto energy levels in an atom. And so this activity is really nice because it's a simple way to show students and talk about, show students electronic transitions in action, but then say to them about how those transitions can be used for storing information. And people, in fact, try to build quantum computers out of this concept. So this is a really, in my opinion, a really nice one that kind of takes students from something simplistic to something really complicated. Okay, so you should have glow-in-the-dark stars. You can also do this with other glow-in-the-dark materials in case the stars, like in case you want to do it next year and you don't have your stars anymore. Next slide. Okay, and again here, there's a teacher guide, a student guide, and an introduction to light and computing. There's also a 5Es version of this one from another group. And there's also, yeah, okay, continue. Next slide. So I'm going to walk you through a little bit like I did before the teacher's guide, but I'm going to go a little faster this time because a lot of the intro slides are very similar, which is why before I was saying it applied to this one and the previous one. Okay, so next slide. So this one, okay, let's see. This one, I just mentioned it talks about the electron transitions. I've mentioned before that it maps nicely onto a chemistry curriculum, but I think there's no reason you can't do this in your physics classes if you are physics teachers as well. And and then I mentioned the quantum computers part. Okay. This again, like before, has connections to NGSS. I think it's a bit of a stretch here on this one, just because I know in the physics, for physics specifically, the physics curricula has boundaries there, but I do think it's still, at least you can say a little bit about the wave particle duality. Next slide. Okay, so we've talked about waves, so we can skip this. We've talked about this concept, and so we can skip this. And you don't need to have done the diffraction one or the polarization one to have done this one. I think these are pretty standalone, but they can build on each other if you prefer that. So again, the electromagnetic spectrum, here's the key point. So building on those ideas of light as a wave, light can have different colors, and those different colors mean different energy. Building on all of that, there's light can also be described as a particle, and the particle is called a photon, and the photon can interact in a pretty specific way with matter. And so if you have an atom, and that atom, you know, it has inside of it, it has internal energy levels that are like a ladder. And then if you, the electrons are configured in those energies, and then if you shine light on an atom, a photon can excite an electron up to an upper energy level. And then after some amount of time, it won't stay in that excited state. So after some amount of time, it will relax back down and emit out a photon. Okay, so this idea that there are energy levels is called quantization. And so the atom here has quantized energy levels, meaning discrete steps of energy. And the electron can only be in one of those energy levels. It can't be anywhere in between. Similarly, the photons are also a kind of a discrete form of light, and they can only have one amount for their energy. So so this concept is what students are going to explore with the glow-in-the-dark stars by seeing how different colors of light or different types of light sources interact with a material that is responsive to light in a very obvious way and kind of a fun way. Okay, so next slide. Okay, so one of the things that students and lots of folks grapple with is this idea that we can talk about light as waves like we've been doing this whole time, but then also switch to this idea that we talk about it as particles. It's okay, both are true, and they're just different different circumstances warrant different explanations that are better in certain, you know, it's simpler to talk about light as waves when we're talking about polarization, but it's incomplete without the particle description, is kind of how I think of it. Okay, so next slide. So this goes over this idea of wave and particle effect properties, and it's more than just a I don't know, a convenient way to talk about it. If we didn't understand light as particles, we wouldn't have been able to develop certain technologies. And it seems that it is a valid way to talk about light, and it's been proven over 100 years of testing and experiments. But it's interesting because matter can also be described not just as particles, as waves. This doesn't go into that, but students might ask that kind of question. So it's important to know that the wave particle duality applies to more than just light. That's like an added tidbit. Next slide. Okay, so I was talking a little bit about this. Here are some more differences. Continue on so we can get to the actual experiment. Let's get to the video. Okay, I talked about this in the beginning, and I talked a little bit about this too. Okay, so you should have all of these, and you have some glow-in-the-dark stars. So this one, again, is going to be happening in the dark. So turn off the lights, and then lay out your stars. And so what you're going to do is put them next to each other, and then you're going to start experimenting with the different colors. So here it's shining this is red. So I think you have a red laser. Let's see what happens. And you get a little bit of, and then you're going to repeat it with the flashlights. Okay. So, oh, there you go. So the UV one should be shining brightly, the brightest, and the LED second, and the laser. So hopefully you were able to see this if you were testing it out at home. And if you didn't see this, then probably the flashlights got swapped. So this will happen every time this way. So next slide. So usually I actually have seen the way that I've seen it be most is have the students do this first and then discuss what happened, and asking them like to predict which one, because I think that works best in this particular thing, because this particular kit, because students will not usually agree on which one should be the brightest, and then they can kind of grapple with that misunderstanding or understanding. And so then, and then I've done this with teachers where they discuss about what's happening as well. And so not all teachers often, know this either. And so it's kind of a fun one that can be surprising. Okay, so then you can do groups of 3 like the other one. Continue. Okay, and this tells you how to differentiate for different ages. Okay, so sorry, go back to the one slide. That one. Okay. So this question of what kind of light comes from the sun. And so, you know from the UV flashlight that the UV is the one that makes it shine the brightest, and that's what's the material reacts to. And so similarly, the sun has UV light. And then this question that is actually one that has motivated a lot of experiments and theory in the first part of the 20th century is, why does it matter how long we shine the lights on the stars? And so, or why does it matter how long we shine? But like, why doesn't a red one, lasers are so energetic, or they're known to be energetic, why shining that on for a really long time still doesn't do anything? Students might ask versions of this question, and it really does have to do with, you have to have the right amount of energy, so the right color light to excite the electrons in the material. That's all there is to it. If you don't have the right color light, you can't make this happen. And so it doesn't matter if you could shine, if you could turn up the power of the red light and you keep turning it up, the most you're going to do is melt the material. You're not gonna cause it to glow, no matter how much is there. Okay, there was a question in the chat. Would red and blue gels work the same, showing blue light has more energy? Okay, where red and blue gels work the same, showing blue light has more energized wavelength than red. If the red and blue gels are the glow-in-the-dark things that I'm thinking they are, then anything glow-in-the-dark should have this sort of feature. I'm not totally sure on the question, Michael. Yeah,
I was thinking that he meant the kind of gels that you put over lights to color the light that comes through them, like in theater or something.
And you can turn off your mute and just tell us what you're thinking, Michael.
Hi, everybody.
Hi.
If I put a plastic red gel over a white flashlight and point it at X, and then do the same thing, a blue gel over a white flashlight and point it at X, would the blue light allow it to glow longer because the blue light's more energized?
So in the case of the stars, the light that makes it glow is UV light. So if the red or blue gels filter UV light, then all it's going to show is like less UV or more UV. But so that's, in this case, it's the UV light.
For instance, when my kids were young, we stuck the different constellations on their ceiling, and there's no UV light coming from the lights in the room. It was just white light, and they would glow.
Yeah, so there
So
is
now-
a component of UV in them.
Okay, so now if I was to do the same thing with a red gel and a blue gel in my classroom, I'm thinking that the red gel will not cause it to glow longer, and the blue gel would cause it to glow longer. Because blue light's more energized than red.
No, I hear
Or
what
am I
you're saying.
thinking?
I hear what you're saying. So in the room case, so the lights, if they're white light, they have some amount of UV light, right? And so what I don't know the answer totally to, so if the electronic transition is sensitive to either blue light or red light, then adding filters will certainly affect the outcome. But I don't know that the stars are responsive at all to red light or blue light. They're responsive to UV light. It kind of depends on how are they at all responsive to the light that you're filtering?
I'm gonna jump in there for just a second. It sounds like this is a good experimentation opportunity, maybe to play with a little bit. I'll also say that when I first did this activity with kids in a couple different scenarios, and teachers as well, one of the things that really, if you start with the phenomena here and just let them try it out, and you kind of hinted at this, Emily, but the idea that the laser, like kids are used to lasers being dangerous and strong, right? And so a lot of kids think the laser is going to be the light source that really makes the stars glow more. And it's not intuitive to them that wouldn't be. So it gives you a good door into talking about what actually is important, what's making those electron transitions happen. And certainly not to change the subject too much, we can return to this question, but I do want to open the floor to questions that anybody might have at this point about all of the activities we've gone over. We do have one more activity. I'm not sure how many folks on the call actually received our expansion pack, received this last year, received the World Quantum Day kit last year, and therefore received the 2D materials activity this year. But I do want to make sure at the very end that we show you a short video that walks through how to do that activity, because even if you didn't get it, the materials are pretty easy to come by. But let's take a few minutes right now to open the floor for questions regarding how to implement these activities. And then remember that we also have a week from today an opportunity to ask questions about what is quantum, and that quantum ask me anything and stump us. It won't be very hard to stump me, but luckily I'll have some help. And I see someone had asked, I know there are a few folks on the call who signed up late. The kits are coming. I'm still getting some materials. I'm not sure I will have them for you by World Quantum Day. I don't know if I can turn everything around that quick, but within the next week or so, you will get them. So you don't have to do these, implement them on World Quantum Day. Anytime around now or even into the future is perfectly fine. So, but I will be following up with some questions for just gathering some information from how these worked in your classroom. So with that, I'm going to be quiet. And if anyone has a question, feel free to unmute. It might be easiest at this point if you do use the hand raise feature, just so we can call on people and keep things going. And then in the last 5 minutes, I'm going to share this video. If you're not interested and didn't get that kit, you're welcome to bounce off, but I will show it so that folks can see that and also ask questions because Jeannie Chips, my colleague, did join the group and she's here to answer questions as well. So I'm going to see if anyone has their hand up. It's kind of hard for me to see that. So if you have a question, you can also put it in the chat.
So Molly, somebody asked if we don't have any kits, will they be coming?
Yeah, so I had a couple of people who signed up a little later because they didn't find out about it sooner. So yes, we will get those in the mail, but I am waiting for some materials to arrive on my end. So it will be in the next week or so. I don't think my materials are arriving till Wednesday, so I don't know if I'll get them out in time for you to have them for Monday if you didn't get it yet. What other questions do folks have? We've got Luke here still, and we've got Jen and Emily who can answer other questions. And I can also move on.
I'll piggyback real quick on the, I don't have my kit yet, but World Quantum Day is coming upon us really quickly. If you go to the Quantime site, we have many activities that are online or printable or hands-on, or are there are choice boards are all posted. The existing choice boards are all posted as well. And so if you wanted to just kind of grab a thing and read a zine or make a thaumatrope, you know, whatever it is, there are those resources there as well. And I will get that link in the chat.
And I will also say it's the International Year of Quantum, so you have the whole year. So I am not seeing any hands raised at the moment. So if folks, like I said, feel free to unmute and speak up, but I'm going to go ahead and share this video for the last activity. And again, this one is if you receive the World Quantum Day kit for the first time this year, you won't have the materials for this, but it is relatively easy to come by most of the materials. There's one thing that you don't have to have, you don't have to have, but it does help if you do have it, which is harder to come by, which is the silicone substrate. But I'll show the video. Jeannie's here to explain a little more too. She's done this activity before. And then at the very end, we'll stay around for more questions. So I think I'm sharing my screen. Here is this 5-minute short video on two-dimensional materials. Can you also
pencil and Scotch tape. These two everyday items led to a discovery that won the most prestigious award in physics. In 2010, Andrei Geim and Konstantin Novoselov received the Nobel Prize in Physics for discovering graphene, a groundbreaking material set to revolutionize numerous fields, including electronics, the medical industry, and energy. The potential applications for this new material are seemingly endless, ranging from targeted drug delivery systems to more efficient solar cells. It can also be used to make ultralight bicycles, flexible electronic devices, and batteries that charge within seconds. But what exactly is graphene? Well, first we need to talk about graphite. Graphite is the same material that is used to make pencil lead. If we zoom into the tip of a pencil, we see that graphite is composed of thin layers of carbon atoms stacked on top of each other.
The best way to think about graphite is a stack of papers where you have individual sheets of paper that are stacked on top of one another. Graphite is very similar in structure. It consists of a bunch of atomic layers. And so if you were to try and pull this stack of papers apart, it would be very, very difficult. But it is much easier to peel a single sheet of paper off of this stack of papers.
So graphene is basically a single layer of carbon atoms, making it the thinnest material in the world. In this single layer, the atoms are arranged in a hexagonal structure, like a honeycomb. Even though graphene is only one atom thick, it is one of the strongest materials. Along with being strong, it is incredibly stretchy. What makes graphene really special is that it acts as a playground to study fundamental physics. It allows us to explore phenomena on a tabletop that would otherwise require massive machines. Now, how do we create the world's thinnest material? The process is actually quite simple. All you need is Scotch tape and a pencil. The process of extracting graphene is called mechanical exfoliation. In this process, a piece of Scotch tape is pressed onto a thick graphite crystal. The tape is then gently removed, which peels a thin portion of graphite onto the tape. However, the graphite is still too thick. We need to thin it further down to achieve graphene. This is done by pressing the tape onto itself a few times. The tape is then pressed onto a small silicone wafer. A gentle pressure is applied onto the tape to aid adhesion. Then the tape is gently removed. If we observe it under a microscope, we can see a few thin flakes of graphene. This pale pink flake might look simple, but it is one of the most important discoveries of the 21st century.
The important factors for mechanically exfoliating two-dimensional materials is that the adhesion of these atomic sheets that come into contact with the tape have to be greater than the adhesion of the atomic sheets with each other.
This peeling also happens when you write. So every time you do your homework, you might be creating the thinnest material in your notebook. Even 20 years after its discovery, graphene remains at the forefront of scientific research. We have come a long way, but more research is needed to integrate it into our daily lives. Scientists are working hard to understand its properties and incorporate it into new technologies. And all of this started with a pencil and Scotch tape. Two ordinary items we often ignore around our household. Sometimes the most important discoveries come from the simplest of objects.
So that is a new video that was put together by some of the researchers on the MSU campus. And I believe, Jeannie, if you want to jump on and say more about this, we had some teacher opportunities to come and work with this lab. So some of the Montana teachers were able to help with this as well in the past. But anyway, you can see that this uses very simple materials and literally, quite literally, is the same procedure they went through with the folks that won the Nobel Prize. Jeannie, do you have anything you want to add to this? I know you've done it before.
Yeah, I'll just point out things about the video that are particularly helpful because I did this when I taught high school chemistry. And what I like is the video walks through what to look for under the microscope, because that was what my students and I struggled with, is how do we know? It all just looks so confusing, right? So the video, them highlighting what you're looking for the single layer is really great. And then they're showing real research that's happening. Yeah, thanks, Molly, for zooming into that part of the video, because it's really helpful for me to know like what to direct the students to be looking at, because not everything you see in that microscope view right now is just the single layer. And so trying to find it, I will say that we do have, what's cool is the people who made this video, they're amazing. Not only are they great at making videos, but we said, you know, I really want a teacher guide. Can you give us extra things for instructors? So we have timestamp places you can pause and add in some anecdotes about what's happening with what the researchers are doing. And there's like a pause right at this second to say what you're looking for, that the thick yellow is bulk graphite, so that's multiple layers. It's really the purple pinkish color that they talk about that become the single layers. So that's always kind of nice, and that doesn't always exist in educational videos. So I'm really grateful for the people that put this one together. And Molly, will they have all of that in? Okay, thank you. You'll share it on the website. Great. So you'll have all those extra resources. to know even more about this video, which is just really helpful.
Yeah, so if you did not receive this part of the kit, and again, it's we had sent out kits last year and we wanted an opportunity for folks to be able to do an expansion pack or get what we had sent out last year, which is why there's some difference between what people got. But this one is fairly straightforward to do on your own. The only piece you would be missing is that little silicone chip, which is, you can see here that they're rubbing onto the slide. And that just helps with the contrast when you're looking through a microscope. So if that's something you're interested in, if this sounds like, wow, I'd really love to do that, let us know, because we may be able to make some more of those materials available. But in the meantime, try it out. We'll share this video. We will share all of the printed resources that you got in your kit electronically. We'll share this presentation today. We will also share, I think, most of the slides that were shared in this. Just wanted to make sure with everybody that that's okay. So all of that will be loaded up onto the website where you initially applied for this kit. Within the next couple of days, bear with me. I was at the STEM Summit last week and gone for a couple of days leading up to this, and we've worked together to put it together. So I want to make sure that all the links are accurate and we've got everything we need. But I will be releasing that hopefully tomorrow for you all on that website, and I'll send out an email letting everyone know it's up there and it's live. I'll probably also keep adding to it over the next couple of weeks because new things are coming out all the time. So with that, I want to be true to time. We're 1 minute over. I do see a question just popped up in the chat there, maybe a couple of them. If you'd like to stay on and continue to ask some questions, even making this an hour and a half, it always goes to the end. So for those of you who want to stay on and chat, we'll be here. Maybe if anybody else any of our other experts are able to stay on for another 5 minutes or so, that'd be great. But otherwise, go forth and teach quantum. I certainly appreciate you all taking the time today and give us feedback. Let us know how we can help you in your classrooms moving forward. My information is pretty much on everything I've sent, but we also have the quantumeducation@montana.edu email that goes to both Jeannie and I. And yes, I will, like I said, we'll stay on and answer questions. I do see someone said they missed the first 30 to 40 minutes. We are definitely going to make this recording live afterwards online, and I'll send out an email with that link. So thank you all, appreciate it. And let's go back through these questions. Have a great evening.
So Molly, there's a question in the chat about algebra. So I just thought I'd say that, so one area of algebra, so you need algebra to be able to learn what's called linear algebra, which some students do learn in high school. It's certainly a more approachable math, I think, than calculus. And so so one approach to understanding quantum information and qubits specifically, so the quantum version of bits that hold information, uses linear algebra. And in fact, there's a whole push in quantum to try to teach like linear algebra and like a linear algebra based approach to quantum much earlier to students, rather than waiting until they have until they're physics majors and also have a whole lot more math. And so I would say my answer is yes. You can say that algebra is a really important foundation for learning what's called linear algebra, and that is it's like a key way that we like do quantum mechanics. It's like one of the main maths we use in quantum mechanics. And so unfortunately, I don't think any of the kits have, and any of the resources we have on our website specifically, use any algebra. I do know there's some introductory material to quantum information science that takes a like basics of linear algebra approach. So it's a good point. It's a good point that we should probably maybe have a more math focused activity using algebra. There is one math focused activity on our website, but it is not using linear algebra or any algebra at all.
And I will also add to that we are the Science Math Resource Center, and although we we tried to lean towards existing activities with easy to ship materials, which is kind of where we landed on the things that we did here, also representing some of the stuff that's going on at MSU. We also do a lot of math, and we are going to be having a math camp on our MSU campus here. There is more opportunity for us to bring quantum into math, just like we're bringing math into quantum, and well, we're focused a little bit more on the science part of this at the moment, but there's definitely a lot of math, and there will be some other resources coming out of our office in the future that will also focus a little more in those areas, sort of on the more abstract side of this. So
to kind of jump right between those two, I can add that we have there's a few of Quandr online games about quantum circuits. And so you're not going to actually see the math, but you can engage with the circuits in doing the kind of manipulations of the quantum state. And so that would be one way to kind of talk about how there's the math that underlies that is linear algebra. But I don't know, we don't have any specific math activities that.
Yeah, in fact, we tried to hide the linear algebra, but maybe we should just.
Well, yeah. I was just going to say, Emily, it just makes me excited to be like, all right, let's write something about linear algebra because there are ones and zeros, and it's like if you're going to do linear algebra, it's a simple place to start.
That's right.
Anyway.
If anybody who's still on, if you have questions, please feel free to unmute and just ask them. You don't have to put them in the chat. I think we addressed most of what folks ask, and it looks like, Michael, thank you for putting a few more resources. There are definitely other resources about graphene out there. We just shared the new one that we had. And Bruce, you have your hand up. Go ahead. You must still be muted, Bruce. See if I can unmute you. I see you, but I can't.
There we go.
I am unable to. Oh, there you go.
Hello?
Now you're on.
We can hear you.
Okay. Now I forgot my question, I think. The gentleman, I'm drawing a blank on his name, but I guess just specifically as professors at research level, say with optics or whatever it is, what balance, so we can teach all kinds of stuff and facts and figures, but I appreciated, was it Colburn was talking about for the 1000th time then I saw it. And so I feel like more and more the best way to teach some of these things is more of an explorative and kind of build the explanation around the phenomenon rather than coming up with the right answer and then saying, aha, see, there we got it, showed you, because we're never really, it takes a while to really understand it. And sorry if that didn't sound like a clear question, but I guess it's more of a pedagogical thought between not getting so hung up on having all the facts right and building a mindset of curiosity in students. And I'll just stop talking there.
I think you're preaching to the choir here. Yep, we agree.
Yeah, I absolutely agree there. It's the first time you see something like quantum superposition, it's probably best presented as look at this interesting phenomena rather than here's something that's going to be on the quiz on Friday. But of course, you all need to make things to give grades for, so I'm sure you could make that happen too.
Yeah, so I appreciate, Bruce, you bringing this up just because it is, so what I've seen, because what we do is curate a lot of these activities from the community of, academics and education folks and professional societies. Some of them are written in a way that is totally exploratory, which is what we want. and I think aligned with how a lot of science instruction has gone. And some of them are written in a more here's all this background information, now we're going to do it. And I think that you have to kind of, I encourage you to pick what works best. And you know, we're trying to provide, like I put an additional link in these things that has more of the exploratory version of some of these activities. And we've encouraged the creators of them to kind of adopt more of an exploratory approach for these unfamiliar effects, but giving people the vocabulary they need to be able to talk about it.
I don't know if there are any questions out there. I'm seeing folks saying that they will be happy to have the recording. I think we have a wide range of background, and I'm certainly one of those who would definitely need the recording. And I am so happy that you all joined us, and that resource will be up there shortly. I am going to stop the recording now so that we can not have it be super long, but I can stay on for a few more minutes.